Hello, my name is Adnan Hamid. I am founder and CTO at Breker Systems. Today, we're going to talk about an automated, scalable approach to cache coherency functional verification for RISC-V based SoCs. In this presentation, we're going to introduce the point that cache coherency is showing up as an emerging and important problem for RISC-V based SoCs. We're going to talk about the planning algorithm strategies we use to generate tests for cache coherency verification and how this work is being influenced by many of our major customers such as Sci5. And finally, we will conclude with some results and some case studies. So why cache coherency verification at all? With these new RISC-V processors, we are building increasingly complex chips with multi-level fabrics, multi-level caches. In addition to the CPUs, we might have other agents that are also coherent. And it is mandatory that we check the data integrity and cache coherency of these systems all the way from simulation to post-silicon. Developing this in-house can be very, very expensive, and solving the problem once that can be used by multiple projects is clearly much more economically efficient. To this end, we have developed the so-called RISC-V cache coherency track app. This automates the generation of cache coherency test cases, generating not only stimulus, but coverage as well as debug information and profiling information. And you will see that we have applied a number of different algorithms to try to attack different aspects of coherency verification. The principle behind planning-driven test generation is we're going to start with a high-level representation of a verification intent, and the bulk of this paper will be spent thinking about that intent. From that, tests will be synthesized, and these tests will contain not only the stimulus we plan to drive, but the checks. It'll compute coverage on what scenarios have been exercised and give us high-level debug information. Once the tests are generated, they can be optimized for whichever platform they need to run it. For example, UVM unit benches, SoC simulation, or post-silicon test benches. The principle of using planning algorithms for test generation is that planning algorithms want to start with a final goal or an objective and be given a bunch of rules about its universe as to how to achieve that objective. And then it wants to form a plan that will lead it to that objective. So we use this for verification by saying we want to hit various coherency coverage cases, and the tool will go generate different scenarios to exercise those corner cases. One aspect of this is that we can kick out various forms of test cases. A popular one is generating C programs to run bare metal systems. We'll talk about how we can also drive transactional test benches such as UVM. Another fallout of planning algorithms is the tool knows enough information to give us a lot of debug output on what the test needs to do and to track the test as it is running to tell us what has failed and what has passed. Okay, so what we have over here at the bottom is a little view of this high-level debug. It also is aware of what it's doing, so we can do performance profiling off of these same test cases. How is this technology being used? Well, at the very lowest level, it can be applied to individual caches. So let's say we're doing an L2 cache with multiple masters, some of them coherent, some of them non-coherent. We can use it to test individual unit benches. A more interesting deployment is to take all the system caches. So over here, we have multiple L1s, multiple L2s, and an L3 fabric, giving us a total of 11 caches. And we can test to make sure that the system is coherent at the entire subsystem level. This is work that was done with NVIDIA. Okay. And the most common use case is to apply it at the full system level, where from the scenarios we're generating bare metal C programs that are compiled and run on the CPUs, and those tests are automatically synchronized with transactions happening on VIPs, for example, to trigger front port transactions. Now, let us focus on the verification metrics that we went after when thinking about RISC-V cache coherency. Most of these features are applicable both at the transactional level, such as a UVM test bench, but some require the actual CPUs in place and only make sense when we're doing software-driven verification. Information is provided to the planning algorithm in the forms of graphs of possible scenarios. And we're going to see a bunch of these graphs as we go through this presentation. These purple diamonds represent decision points in the graph where the tool can make a random decision on where to go next. The blue boxes represent sequences where it must do all the children of a node before it can move on. Yellow octagons represent hierarchy, so you can double click into one of those and open up a node. And when you double click into a node, then you can see the module boundary around it. Ultimately, what is happening is the paths in the graph represent the possible different test cases that the tool knows about. And when you go measure up the total number of scenarios the tool knows about, you realize that these ends up being very, very large numbers. Okay? So at least at the point where this picture was captured, the tool had some 10 to the 45 possible scenarios that it knew how to go generate for various aspects of coherency. And clearly we cannot run all these scenarios, but it gives you a sense of the richness of test cases that we can go after and the volume of tests that could be run, especially when you get to post-silicon. The first piece we're going to delve into has to do with covering the state space of the cache lines themselves, the various cache states. I think of this as an algorithm that has one address with many masters. The basic principle is the tool will pick a location in memory and then synchronize or orchestrate multiple masters to hit on that location with different forms of reads and writes to force different transitions. The way the planner ensures that it's hitting every possible transition is it in fact starts with the coherency protocol implemented by the design. So over here we have a simple state machine for a 5-state Moisey protocol. And it turns out a state machine like this is a graph and can be mechanically transcribed into a graph for the planning algorithm. And from there, the tool can generate interesting sequences of transitions that are orchestrated across masters. For example, CPU 1 might do a load, which would leave us in a unique clean kind of state. Then CPU 0 might do a store to the same address that would leave us in a shared dirty state. Then maybe CPU 1 would do a load exclusive kind of operation that would get us into a unique dirty state. And then we might have some front port VIP come along and do an exclusive store kind of operation that presumably would force the data to be sent out to memory depending on the coherency protocol. Okay. Each of these arrows represents a producer-consumer dependency that is both automatically inferred by the tool and automatically enforced by the tool. And then what is happening is we are generating multiple such scenarios and co-scheduling them to create a complete coherency mess. Right? So what is happening is we are true sharing within these scenarios and we are false sharing across the scenarios. So you might have CPU 0 and 1 trying to take a cache line through one set of transitions, whereas CPUs 2 and 3 might be trying to take the same cache line through a different set of transitions, and the poor cache line is bouncing all over hardware, and at the end of this presentation, we'll see the results of such traffic. So when the translation of the coherency protocol into a graph is an automated process, and when you look at the graph, you end up with nodes for each states and nodes for each transition. You have reasonable control over biasing which states you want to go after. For result checking, every read will be checked to make sure that it returned the expected data. So the tool is scoreboarding and tracking memory as the tests are generated. And we're able to measure coverage not only on which states have we tried to get to, but which state transitions have been done, or even say pairs of transitions or triples of transitions, right? Depending on the size of your design, this might get to be a very large coverage space, but from a computational standpoint, it is all very tractable. Sharing cases. When we have multiple CPUs in the design, it is easy to forget that we have to think about sharing states not only just across 2 cores, but across 3 cores, 4 cores, across all the cores, having the data in various different caches and so on. So to that end, into the graph is built-in specific logic to thinking about how many Snoop edges to trigger on a particular operation for reads and writes, whether these snoops come in from other CPUs or they come in from external interfaces such as a VIP or a third-party master and so on. We can control how many snoops we want, whether they come from CPUs or external masters. Every snoop will be data checked to make sure the return data is correct. And we can measure how often we have gotten snoops from various agents. Next thing to think about is who is providing those snoops, right? They may come from another CPU in the same cluster. They may come from another cluster. They might come from another chip for designs that involve multiple boards, or they might come from a coherent master such as PCI Express. So these decisions are also built into the tool, where the tool can make decisions on which options to go after. And again, we can control the likelihood of different masters triggering those snoops, and we can measure how often different masters have driven snoops. Next thing to think about, we have to worry about all the possible operation sizes. So of course we have the 1 byte, 2 byte, 4 byte, 8 byte operations. They're the larger special instructions that might be 16 bytes. And there are also block operations where maybe we want to take, say, 1,000 bytes through the same coherency transitions, simply because that allows us to do tight loops of code that'll fill up all prefetch buffers and all write-back buffers. The different size operations again show up in the same graph, where the tool is choosing how big the operation should be. Again, we can bias or constrain out certain options. Every read is checked, and we can come back and measure to see have we done every possible size. False sharing is the important trick in verification. We want multiple concurrent scenarios to hit on different parts of the same cache line, so that hardware has to assemble that cache line from different caches. So the idea over here is the first scenario might be having multiple agents beat on the first 2 bytes of a cache line. The next scenario might be working the next byte, and the following scenario might be working on the next 4 bytes. These scenarios are all taking those bytes through the different state transitions per the transition table we saw earlier on, but they're picking different paths through this transition table. And of course, hardware has a heck of a time trying to keep up with everybody's requests, which is a beautiful thing. Next thing we care about when we talk about cache lines is making sure that we can cross cache line boundaries. We want to do fetches that transcend the boundary of 2 cache lines. Often, if we can get those cache lines, can end up in different caches, and hardware has to fetch both lines before the operation can carry on. So this is trying to show a little picture of 2 different cache lines and having a store that hits on 2 lines. Related to this problem is capacity eviction. So we want to get not only drive the invalidate instructions that'll cause software to evict a line from a cache, but to get enough hits on the same index in the cache such that cache lines have to start getting evicted. So traditionally, all of these things are very difficult to hit in verification, but one of the things that the planner does is not only schedule tasks across different CPUs, which is what we're doing to do the different transitions, but also schedule memory for each of those operations. And the memory scheduler is oriented towards allocating things on strides so that we can get these eviction cases. Another perennial problem with weakly ordered memory systems is memory ordering tests, where we got to ensure that when memory barriers are in place, that memory ordering is properly enforced, although the rest of the time for performance, we want memory to be weakly ordered. So it turns out the mechanics for how tasks coordinate with each other to enforce these producer-consumer relationships always involve a flag, right, and involve a barrier. So these barrier litmus cases are being tested on a regular basis as the tests are running. Decker is a custom algorithm designed to test for weakly ordered memory. It is one of the different litmus cases that we think about, and Decker has been scaled up to multiple processors, and it's one of those tests where things are all good unless all the loads see an initial value and not one that was stored by a different CPU. So these operations are done randomized across all CPUs, all operation sizes, all kinds of load store sources, right? So we are doing the memory ordering tests from every possible agent with every possible type of transaction. WFE, WFI, so wake from event, wake from interrupt. These are more power management oriented tests, but they play into coherency because we got to be making sure that our cache retention policies are working right. So the test will generate scenarios where one or more CPUs are put into a WFE state, and but making sure that at least one is left awake to wake up the CPUs. Memory workload is yet another scenario. This is more, I think of it as one data set that is moved along around the design to many addresses. It is conceptually simple and allows the CPU allows us to put a tremendous amount of load on each CPU as it is asked to either move data or compute checksums of that data. And it's a good way to put a lot of heavy stress on the design that is interleaved with the rest of the coherency scenarios. And then, of course, all of these different scenarios are being run concurrently, leading to lots of heavy verification scenarios. How good are these test cases? So this is data from, in fact, ARM-based system, but this is looking at ARM cycle-accurate simulations. And we were able to profile what was going on just the coherency channel of the ACE fabric. And that means that the reads and writes have all been filtered out, right? And we looked at the results from a very good coherency-oriented scenario that was created internally by the customer. But when you compare that to the traffic that comes off of the Coherency app, you see that there's a big storm of coherency traffic running around the fabric, which is not completely surprising given the strategy of getting many concurrent coherency scenarios running at the same time that are trying to false share on the same cache line during different states. So why would anyone care about doing this, right? So we're going to look at two case studies. The first one is oriented around SoC simulation. And the key points are that instead of spending months and months and months coming up with scenarios, the tests were generated very, very quickly, and we're able to get to much higher coverage than the internal test cases could. Another one that I think is interesting is a post-silicon application. This is Cavium, now Marvell. They were building chips with 48 CPUs per core, and they could gang multiple boards together into one system, and we were verifying 144 cores connected with coherent fabrics in post-silicon, all off of this Coherency app. The RISC-V Coherency app is just one of the apps that we've been working on. Each of these things, of course, come about in partnership with our customers. So the RISC-V one has been developed in conjunction with Sci-Fi. We have a similar one with ARMv8. There's a cache coherency app that's architectural neutral, so good for things like DSPs. There's a security app to check security where hardware is the root of trust, right, HROT. And there's a networking app that's organized around packetized data and things like Ethernet and 5G and so on. So to summarize, cache coherency is becoming a major problem for RISC-V based SoCs, especially the larger ones. We're using planning algorithms to synthesize test cases for these for such systems, and so far the results are showing very, very high coverage for very complex scenarios, allowing us to find and correct bugs much sooner. Thank you very much.